This is an assessment that I've been using for the past several years for my AP Calculus classes. One of the things that they have to know how to do is to find the volume of solids of known cross-sections. And in this project I have them build a model so they can see what is going on, and it helps them to visualize and solve the problems better. So this is for Advanced Placement Calculus, AB and BC. I have mostly 12th graders. Some 11th graders actually take the AB and BC classes. I think I've got 2 11th graders in BC this year. There are no TEKS for AP Calculus, but the College Board has published a course description, and in it, one of the topics under applications of integrals, they have to provide a common foundation. Specific applications should include finding the area of a region, the volume of a solid with known cross-sections, the average value of a function, the distance traveled by a particle along the line, and accumulated change from the rate of change. And this can be found on the AP Central website. I've looked back through all of the free response questions that I have, and they go back, I probably go back 15 or 20 years, and there's been a volume problem on every one of the tests. One of the 6 free response questions is always a volume problem. One thing that's missing from the course description now is volumes of revolution. Doesn't mean they're not testing it anymore. They just consider that to be a solid where the cross sections are circles. One of the reasons this topic's hard for the students is that it's hard to visualize these cross sections and what these solids actually look like, and they're even harder to draw. So unless they can actually develop a picture and see what they're finding the volume of, they have a lot of trouble finding the volume. These models are going to help them with this. I've been doing this, I started this project about 12 years ago. I add to it, take away from it every year. But the students always seem to like it, and they seem to know about it before we even get to it. And they are always asking when they're going to get to build the models. And I believe it's helped. I have almost 100% of my students every year get 8 or 9 points on the volume problem out of a maximum of 9 possible points. Pretest that I usually use is a problem similar to this. It may be this one. I may change the base. Instead of using a circle, I may use parabolas. But I have them find the volume if the cross sections are squares, semicircles, quarter circles, equilateral triangles, isosceles triangles turned different ways, and rectangles. The Calculus in Motion website has a program that Audrey Weeks has developed that I use when I'm introducing this to the students, and I thought I might show you that. It kind of helps them see a little bit of what's going on. If I can get to it. This uses Geometer's Sketchpad. And after it loads, alright, so we can see here we've got a base. It's a circle with radius r. And what we're going to do is in this one I'm going to fill it with squares. And I can show the chords on the circle. And each of these is going to represent a square, where this would be the base of the square, and the square itself would actually come out of the screen towards you. So we're going to have a bunch of squares. Each of them is going to be a different size, and we're going to completely fill this circle with those squares. So I can lay this down flat so it'll be easier to see and look at some representative squares. what we do, if we imagine each of these squares having some thickness, then the students would be able to measure each square, find the area of the square, multiply by that thickness, and so find the volume of each of these square prisms. And then if they find the volume of each one and they add them all up, then we should have the volume of the solid. And that's where the calculus comes in, is that width we're talking about. We let it approach 0, and then to add them up we do a Riemann sum, which is just an integral. And we can actually watch a square as it goes through. You see how it gets bigger, then it gets smaller. Shows over here the area as the square changes size. And let's see what this solid looks like. And so we can see if we had a circular base and we filled it with square cross sections, we'd get a shape something like this. We can actually see the square. And we can see over here the actual total volume would be 42 2/3. If we slide that square, we can actually watch as it integrates. It's adding the area of each one of those squares, or the volume, when you multiply by dx. And the total is 42 2/3. Okay, we can do other shapes. If I have another circle, we'll drop it flat. Maybe I want to fill this one with equilateral triangles. So let's actually create this solid. So what I do with this, I use this, I show the students that what all we really need to know is how to find the area of that cross-sectional shape. So we'll use formulas from geometry. For equilateral triangle, it would be s squared over 4 times the square root of 3. And that s is actually the base, or one side of this triangle, which is the distance across its circle. And so that would be the upper part of the circle minus the lower part of the circle. Square root of r squared minus x squared minus the negative square root of r squared minus x squared. So we would put that into the formula for where s is, square it, divide by 4, multiply by the square root of 3, and then integrate it. And we come up with total volume. And maybe we wanted to do isosceles right triangles. And let's see what this one might look like. Okay, and there's what that one would look like. And we can see the triangles. And the base doesn't have to be a circle. Here we've got a base that's a right triangle, and maybe I want to put semicircles in it. So it kind of look like half a cone maybe. Okay, so there's our solid. And finally, maybe you've got a tetrahedron is a right triangle for the base, and you fill it with right triangles. And we can see that. Okay, so that's how I pretty much introduce this and show them how to find the volume. And then I hand out the project assignment to them. Okay, I give them some equations to define the base of a solid, maybe a circle, maybe some other shape. And then their job is to construct that solid using the base they're given, and each of the groups that I have is going to be assigned a different cross-sectional shape. Some of them get squares, some of them get rectangles, some of them get equilateral triangles. I require a minimum of 8 cross-sections. They must measure each piece and use geometry to calculate the total volume of their solid. And I assign the groups. I don't let them pick. I'll take the top 4 or 5 students in the class, make sure they're each in a different group, and assign the rest randomly. Now, they can use anything they want to build the model. Most commonly they use wood, styrofoam, plywood. I've seen some made with Legos. Had students one year make a project out of bread. That's not really recommended, but I'm not going to tell them they can't. If that's all they can afford for materials, then that's fine. I don't want the cost to be an issue. When they finish on the due date, they have to present their project to the class. Every student must participate. They must include their calculations and interpretations of the results. Here's the rubric. I know that's really hard to see unless you get real close. It is in the Word file that I've attached. What I mainly look for is that the base is the right shape, cross sections are the right shape, the model's scaled accurately, there's a minimum of 8 cross sections, they accurately measured each piece, calculated volume geometrically, then they have to calculate volume using calculus, then they have to compare the two, and I want to see them mention the limiting process of calculus using an infinite number of cross-sections to get the exact volume. Formative assessment, we're working problems this whole time. They also report weekly on their progress, show me their calculations and what they've completed. Their final grade is a combination of their presentation and their grade on a post-test, which is, I count each of them as 50%. Post-test, I use previously released AP exams, pick questions off of those. I won't put them on here because of copyright reasons, but you can find those at the AP Central website. And that's about all I've got. I've got some pictures of some models students have built the last few years. The last couple of pictures are the ones that got the highest grade this year. Here, these were rectangular cross sections, and they actually made it look like a little mountain with snow on it. This one was cross sections made out of equilateral triangles, and these all have a circular base. Here's another view of that one. This one was also equilateral triangles on a circle, and this was made out of styrofoam, and it hasn't really held up too well over the last couple of years. Here's another one made out of wood or plywood with circular base and semicircular cross sections. And here, equilateral triangles again. This one had a semicircular base. And the one that had the highest grade this year is the Aggie Bonfire, with their burning desire to receive an A on this project. And that's all I've got. Thank you for listening. And see you soon.